mobile. That's True Skate, also True Surf, a few other games you might have heard of, jet car stunts. Anyway, big things, all mobile. So, and how I got into games was through programming on my own, learning on my own as a hobby. And I'm here to tell you basically about how to get started on that, how to progress on that if you're already working on it, and also sort of maybe pike your interest in various areas of hobby game programming and how it can help you in other fields as well, because the technologies and the techniques that go into programming video games are relevant in many industries. So, let's start first of all, well, actually a little bit more blurb. So here's a bunch of games. So a few of these you probably already know were programmed by one person as a hobby in their own time. They're at high speed, it's not as important. You know, the website or whatever, the refresh rate, you don't even control it, it's just typed by the browser. A lot of other programming, sort of application logic, you're not going to be controlling the render, but in games, the render is king, the speed is king. More important than anything else is how fast your project runs and how fast it renders. You've all obviously played games and been like, oh god, I can't play this, the frame rate's too low, and you have to put all the graphics or whatever. That's really the crux of all game programming is speed. And the start of it all, like I said, is the render loop and the game loop. So, we have two separate loops that are always running in every single game. In one loop, you're just rendering the objects as fast as you can. That loop needs to run at the maximum speed it can run, because some people are running, you know, computers at hundreds of frames a second. You've got to be updating constantly, hundreds of frames a second. The other loops where you do your game logic, like, you know, when a ball hits a wall, it bounces back. Here's a quick example of why frame rate's important, obviously. Slowing down and speeding up. These are different refresh rates and different frame rates, which are directly tied to what I was talking about with rendering. So if you're rendering slower, things appear choppier, it's sort of unplayable. But an important part of this too is that even if the render is slowed down because someone has a slow computer, the logic shouldn't also slow down. It shouldn't also be tied to the render. That's why we have two separate loops. Here's a quick example of some code in JavaScript that I wrote for an engine I was building. We have a generic game object class, which we'll come back to again later talking about that. But basically every single object in the game that is rendered by the game and is used by the game has a task that it will complete on game tick, which is basically a cycle in the game's logic loop. And it will also do something in its rendering, which is not visible there because that object doesn't have render code in it, but you can see there we have a separate loop for rendering where every single object is rendered. And like I said before, these loops are running at different speeds. Here's another example, slightly more complicated, of the exact same thing. This is a Tetris game I coded in C++. It's the exact same situation where we have a render loop and a game loop that are separate, and what I'm trying to get across very importantly here is that every game will always have these two loops and they will always be separate. There may also be a third loop, and we'll get into that in just a second, but you'll always have these two loops because you have to have your logic and your render speed not tied together. You'll always notice here as well, the top loop there, our game loop, is just running as fast as it can as well. I didn't tie it down on this one, probably should have, but we have a game speed delta thing. What you're doing there is each time the loop comes around, it may have taken less time or more time, depending on the speed of the computer, other things going on in the background, stuff like that. You can't have your logic tied to how fast the loop's running because it might not run at the time you want it to run. So you need to decouple everything as much as you can. By using a delta, the amount of time it's changed between the last loop, you can affect the physics differently. You know, if I drop a ball and it takes a second before the next frame's rendered, we don't want it to have just when they move slightly. We want it to actually be down at the bottom now because we add a whole second's worth of gravity to that rather than 0.1 of a second, which is what we're assuming with the loop. So, talked about that one. Why we have the two different loops, and the third loops that I was going to mention before is the interrupt. So the other thing games do, which a lot of other programs don't have to do, is deal with user input, which can be happening outside of your game loop or your render loop. If you're dealing with the game speed at 60 frames a second or something and someone presses a key in between that, you don't want to just discard that key press. It'd be ridiculous. So on top of that you have interrupts, which are going to be more important than your game loop or your render loop, even if they're not acted upon until the next game loop. You register the input, you save it, and then you deal with it later or next time you can. But that has to be captured immediately. Here's an example of when it goes wrong. That should have autoplayed, it didn't, I'm kind of sad. You guys remember Fallout 76, right? Hilarious. I love that game. I never played it, but I love it, how bad it was at launch. This was Bethesda slapping a multiplayer component onto their single-player engine, and part of the feature of the single-player engine was that the frame rate and the logic loop were tied. They tied their render and logic loops together as part of the entire engine-based foundation, and the result is that if your frame rate is higher than someone else, the game runs faster for you.
Oh my god. Why is he my game has just started running at 2 times speed.
Normal, it's all quite normal.
Well, you come through this door, Tom.
It seems fine to me. I don't know what you're talking about. No, it's absolutely fine. I don't.
What has happened?
What happened, as I tried to explain to you. So I'll try again, because I might not be completely clear enough yet. This is a very important point. The game logic in this case is tied to the user's frame rate. It doesn't have a delta variable or something like that is happening deep inside the code. I'm assuming it's more complicated than what I'm saying now, but this is the general gist of it, is that somewhere in the game, it's just saying every single loop, increment things by a little bit. Increment the physics, increment the animations, whatever. But that loop is tied to the speed that the game is running, rather than just time in general, using a delta. So if you have a fast computer, the entire world just runs faster for you, which is ridiculous in a multiplayer game. And it's amazing that that even worked. So now we'll talk about performance, which I mentioned before is more important than anything in a game. And this is one of the main things about game design above, or game programming above any other form of programming. Well, there are certain other places obviously where performance matters, but in a game, performance is more important than like accuracy. Who cares if, you know, the physics is slightly wonky? If it runs a bit slow, that's not going to be good enough. So there are two things that have to be optimized in every single situation, because we have the two loops, the logic of the game and the rendering of the game. The logic is going to be completely under your control, basically, because you're writing the logic as a programmer. The rendering might not be. Sometimes the rendering is because the artist gave you a model that's really inefficient, and you can't do much about that. Other times, you're using a third-party engine and it's doing things that are out of your control. If you're writing your engine yourself, or if you're writing everything from yourself, you can optimize both, but generally logic is what you're going to be optimizing the most. And what I'm trying to stress at the moment with these next few slides about performance is that the performance fixes you should be doing, these ones, are structural. So the code, oftentimes you'll write something, you'll write a program, and you might have done this at uni in a few courses. You'll go back and optimize loops by unraveling them or stuff like that, you know, sort of micro optimizations. Really in game programming, it's more about higher level optimizations. You're going to be doing like big refactors of entire concepts just to get a bit more speed. You're going to be designing data structures that are weird and convoluted, but they run like 2 seconds faster every time they're trying to do something. You're going to be using like obscure maths that no one else uses in any other field, just because you need that extra frame of speed at any chance you can get it. So micro optimizations are part of what we do, but really more important are these macro optimizations. You're going to be the entirety of the game code ecosphere is based on incredible speed that you can get out of using things. So one thing I'll say is if you're at uni and you wanted to get into games, well, good courses are ones that focus on optimizations. So AI is one of them. Another one is any algorithms and data structure courses like that. That stuff's just like foundational to write anything in a game. You can get kind of far by just writing like if statements and for loops, but you'll eventually, everything will just kind of slow down and stop, because you'll be doing so much every frame, so much every logic step. You need things to be crazy fast. But also, as you've always heard when people talk about optimization, only do what needs to be done. And that just comes from experience. So you just got to try. You know, you can't know ahead of time what's going to be slow and what isn't. You can kind of guess, but you can't know for sure. So only do what has to be done. And optimization tip number one, group things into chunks. This will come back again later. On the next slide, I'll talk about it more. But also, just as a quick overview on that, to speed things up, do large operations on a lot of things at once rather than looping through things one by one. So, like I said, we'll get into that in a second, but that's the main optimization tip. And the second one is learn by trying, as I already mentioned. So you might have already done a course on, I think it was algorithms, or it might have been AI. One of the courses talks about binary search trees. You guys know binary search trees? Yeah. that's like your foundational optimization technique you're going to be using everywhere. This is a picture I stole from somewhere, a binary search tree that's showing off how to construct a quad tree, which is a way that you might have also already known about that, but it's a way that you partition a 2D space into quadrants so that you're only storing higher level information rather than the position of every single object. You can just store the quadrants that objects are in, which massively reduces the amount of computation time it requires later when you need to find an object wherever it is. Or, more specifically for games, if you need to check collisions and things like that, see what's near you, way faster to use a binary search tree where you can skip like entire quadrants of the search tree every single level. So if you're in the bottom right quadrant, if you're that red square, the first step of the binary search tree, you cut out 3/4 of the entire system immediately by just jumping down whatever layer that is. Wouldn't be possible to do physics, wouldn't be possible to do collision checking without things like that. So binary search trees are abstracted further into oct trees in 3D space, which is the same thing but with an extra dimension. And we'll get into 3D programming later. It's pretty fun. But the thing is, it's exactly the same as a quad tree, just with an extra dimension. But as I said, it becomes vital, like life-saving for writing any sort of code that deals with finding other objects in an area. It just would not be possible to write physics, as I said before, without using oct trees or extreme optimization techniques for partitioning space, like an oct tree. So that's a lot of crap I've talked about already. Render loops, logic loops, performance, oct trees. What if you don't want to write all that crap because it takes too long and it's too complicated? It's fine. There are systems, hopefully they'll make programming games easier for everyone. One of them is, one part of that is that we're going to be using, generally everyone's sort of agreed on the system called ECS. So if you've heard of engines like Unity and Unreal, you might have heard of the phrase ECS. They used Unity and Unreal ECS engines. ECS is a programming paradigm. So if you know, I think they used to teach it in CSS 2002. I'm not sure if you guys still do it or not. We used to learn a system called MVC, Model View Controller, for websites and for applications, where you have a model view and a controller that each have their own sections of what code they're dealing with. ECS is the same sort of thing, except not the same acronym because it's a different concept. But it's the same sort of thing where it's a paradigm. So it stands for Entity Component System. And I have a picture there of this guy because this is the first game where developers tinkered with this system and got it laid down. I think Apple was the first company to like write a paper on it and make it an actual thing. But Operation Flashpoint in the early 2000s, I believe, was the first game where the developers were making this a proper like structured system. Interesting note as well about Operation Flashpoint, it has a scripting language in the game and people code golf with it. Apparently you can like manipulate it by climbing ladders at certain speeds and stuff like that. It's really stupid, but it's out there. Anyway, so entity component system is, you're going to have an entity. So I showed before that code I had in JavaScript where I had a thing called a game object. And you notice, you might have remembered, it had like nothing in it. It was like basically empty. That's your entity. And like I said, Unity and Unreal, they all do this, and every modern game engine really does this, where you have the basic concept, like your atom is an entity. It's just something in the game. But every single entity has an ID, and that's basically it, a UUID, and a few interfaces maybe. Then you have a component. So a component, if for an example, a projectile or something like that, or car, or a physics object, or natural object, whatever you want, and that's sort of like a tag that you just apply to an entity. So entities can have multiple components on them. They could have one, they could have none, they could have many, whatever, it doesn't matter. And finally, a system, which is a game system that functions on your components, e.g. physics. So, for example, you might have a physics system in your game, and that will automatically, well, you would have written it to go through and deal with every object that's tagged as a physics component, every entity. Why has this system been invented? It avoids dependency hierarchies, which is a massive problem you'll probably get into if you start running your own games using a classic programming paradigm, where you'll have game object, then you'll have like a subclass called like, physical object, another subclass like drivable object, and the subclass car. But then it's like, oh, but what if I want my car to also be a sound emitter? Multiple inheritance, maybe. Multiple inheritance gets pretty weird, pretty wonky, and it's very difficult to sort of, you guys know multiple inheritance, gets wonky kind of like doing it live as well. You can't really like chuck things together that easily. It gets just weird and strange. Components are more like like I said, tags, and it's just systems that run on components independently. So you can throw things, you can give something a component, you can take a component away, you can throw things in and out, and it's runtime extensible, it's fast, and it's just great for, well, basically everyone's just decided it's great for games. That's what we do. So now I will talk about engines, because we just talked about ECS, which engines use, and I was mentioning how games are sort of, there's a lot of like foundational stuff that can take a while to get through. Writing random loops, writing logic loops, writing optimisations and stuff like that. I want someone to do all that for me, give me an engine. So you've probably heard of the classic engines, Unity and Unreal. They're the biggest ones at the moment. Both ECS, both free at the moment, I think. Unity has a reputation for being more for like indie games, and Unreal has more of a AAA reputation, but they're pretty similar. There's also like a ton of random other engines that exist. Most game companies will have their own engine, or they will run an extended version of someone else's engine because they've customized it to what they want. Do you know all these engines? Probably not, maybe? Don't know. So, what are engines good for? Content management. No one can be bothered dealing with loading in textures one by one, loading in sounds and things. You have an engine for that. Render optimization. So rendering is the core of games, as I mentioned. It's getting things to run really fast. Thousands and thousands of dollars go into this. It's like cutting edge research. Very, very smart people work on it. Those people, their technology gets bought by engine companies. So you can write your own render stuff and you can get it working pretty well. You'll never get it as good as like, a AAA studio that's paying millions for like some, genius guy who's come up with some incredible system every year. So generally, engines will have better renderers than you can write on your own. I/O and OS management, because again, who wants to deal with like Apple or Windows if you're an Apple person? Who wants to deal with having their game work on every system if it can be done by someone else for you? But here is a catch. This is a good thing. Engines are great for non-programmers, and a lot of people making indie games these days are non-programmers. They have an idea and they want to make it, and they go to an engine. That's great. You can go on YouTube and watch tutorials, and you can get basic scripting done. You can buy scripts from other people. That's all great. This talks about the actual programming, and I'm assuming you're all programmers. This is a trap, because you might find engines are really unintuitive if you're a programmer and you're coming from a programming background. Unless you know what you're doing and you've already tried all this stuff before, you might open up an engine, you might have already done this, and go, oh god, why is there like a film style, like, timeline at the bottom? Why can't I write a loop the way I want to write a loop? What's all the script stuff? Why do I have to like do this weird, it can be a bit of a mess. I'm a proponent of do it yourself first until you know it, then use an engine. Because you can be like, okay, now I know what I'm doing, I know what all this stuff actually is, and I know what's going on underlying, what's happening underneath all this glitz for the non-programmers. So you have a better way of you can get more out of it that way. So, quick change of topic completely into shaders. You've heard of shaders, right? Maybe you've been scared by shaders. They're a scary idea. And they're written in a language called GL, which is like C, and C is scary. So, and it's like weird C, so it's not good. Yeah, that's Minecraft, as you all know. Minecraft shaders, you would have seen them before. How do they do this? Because the point with a shader is that in a Minecraft shader, for example, they don't change any of the geometry. The water appears to have waves on it, like it appears to be reflecting water in a special way and all that stuff. But fundamentally, in the actual game, it's still just a flat plane. There's no change in geometry. So the way that shaders do all this, oh, that was meant to be one by one as well, but whatever. Yeah, so basically, shaders are what your $1,000 graphics cards are for. And as I was saying before, rendering is like the cutting edge where all the money goes into games. Specifically, it goes into shaders and the API, Vertex API layer, which is going to be what shaders are working with. So there was also Direct3D, because I mentioned GL. Direct3D is the competitor, the Microsoft competitor. I think they're about equally used, but I've only ever written GL myself, so I can't really talk about Direct3D, I'm sorry. But they have basically the exact same structure and functionality. There are two shaders, your vertex and fragment shader. The actual pipeline for a shader is a little more complicated. I'll quickly jump to the next slide so I can show you. That's what the pipeline looks like, but you won't deal with any of that except for vertex and fragment shaders. It does other smart stuff outside of it, assembly and rasterization, and then frame buffer optimizations, which is just stuff to do with reusing frames that they haven't changed. But I should start at the top. So the pipeline is, you write code that has 3D objects or whatever, manipulated, or 2D objects. You send it to GL, you pump it through as a matrix of transformations. GL turns that, it rasterizes it, turns it into like actual images of pixels. Then it sends it through to the next shader section, which is the fragment shader, where it then applies color to all those pixels. And then it pumps it through to the GPU. And the GPU takes the raw numbers, just throws it on the screen and caches it, and it hasn't changed the next time and uses it again. So the point of a shader is, the pipeline for shaders and this whole graphics API pipeline is to take the matrix transformations of the objects that are visible on the screen that you're giving it and make actual things appear on the screen correctly positioned, projected, textured, whatever. So yeah, there'll be two parts of it that you would be attached to. They're either the vertex shader, if you want to, yeah.
What about geometry shaders?
Yeah, so that's basically a vertex shader. It might have a different name. Was that in Direct3D you read that, or somewhere else? Okay, well I haven't seen it in GL, but your vertex shader is like essentially a geometry shader. Oh, I have a link here that I'll quickly click on. I don't know what this will do inside the slides. Oh, there you go. This is just a sphere. There's actually nothing changing in the geometry except the shaders. Every single frame, the sphere, every point on the sphere is getting rendered and going through the vertex shader. It runs in parallel as well, every shader, so that the graphics card just takes this massive amount of info and just pumps it through like 100 bloody, what do you call them, little channels, threads, yeah, and just throws it out at incredibly high speeds. It's super optimized for doing this sort of thing. This is what it does. This is what your GTX 1080 is for. What are they up to now? 3080 or something? 3060? Yeah, sorry, I have a 1080. It was like years ago I bought it. It's top of the line that I got it. And then the color shader is doing the exact same thing. The fragment shader is doing the same thing with the colors there. But even without the colors, the geometry is not changing. It's just the way it's rendered. This is way faster than doing this in the actual geometry. If you were going to replicate this with just geometry, like you were actually deforming a sphere in real time, this would run like half speed. It's so much faster just to throw it on the screen as how you want it to look and leave the actual geometry. Like if you could see the Y mesh, it would just be a sphere. Leave that completely unchanged because, as I said, GPU is incredibly optimized to do this. That's why you have a GPU. It's just for shaders. So I don't know if I can go back to this slide now. Full screen. Good, cool. And that's why I have that thing that it just says performance, because that's what they do. So here's an example of some shaders that I wrote. This was just for rendering water, like really basic 2D water. Almost nothing in the vertex shader because I just want it to be flat. And I have a bunch of stuff in the fragment shader. Now you'll notice something right away is that there is no syntax highlighting on this code. And that comes back to what I was saying about shaders being really hard to work with. Notoriously hard, because they just output directly into the graphics. There is no like console, there's no output, it just goes straight into graphics. If you make a mistake, you just get a black screen. You don't get any indication of what's actually happening. I think there are some third-party tools you can use for debugging shaders, but really it's just going to be up to you. So what most programmers do, what most game devs do, is they just output like colors to represent data. So like, oh, if this number's 4, output red. And they'll be like, okay, it's actually 3 because I'm getting green. So yeah, you're never going to have a good time working with the shaders, but they are super, like they're more important than anything. And like I said, it's in sort of like a weird version of C. So you're just going to be reading like, you know, the shader online information every time you're trying to write any shading stuff. Let's jump to 3D programming now, which is related to shaders, because all 3D programming is shaders. It goes back to the vertex shaders. You're going to be pumping, like I said, data just through the shader, and it will handle the actual projections of the stuff. Unless you're doing that yourself, which I don't recommend. You would have heard of like triangles, poly counts, and stuff like that. It's relevant for models, and it's relevant for you because you would be trying to write the code in such a way that you're sending the least number of triangles through to the shaders at any time as you can. Because again, performance, more important than anything. So 3D maths itself, if you're programming in 3D, is just trigonometry, which you might expect. 3 dimensions, 3 bloody, what do you call them? Points on a triangle, everything's trig. Distances between things is trigonometry, angles between things is trigonometry. And then that comes into vectors. So obviously, that's a vector. No. I don't know if they will get that joke, but yeah, got him. So do you remember vectors? If you did Maths C at high school, or if you did some courses at uni, like maths courses, vectors? Again, vectors are something you might not touch in other parts of programming, but it's like your life in game development. If you're doing 3D programming, if you're doing 2D programming, they will still come up. If you're doing stuff like anything to do with movement, velocity, we're doing a little bit of vector stuff. But 3D programming, it's your life. Like everything is a vector. Just position, direction, velocity, and then your 3 coordinates. And you're going to be adding vectors, removing vectors, and we'll come back to that a little bit later as well, because they're relevant later. Ray tracing, which unfortunately has been co-opted by in ray tracing and pop culture. Everyone now thinks of the super high-powered rendering that NVIDIA is doing. Like, have you seen that? Lighting with it's like, oh, it looks so good, physical lighting. They call that ray tracing. But ray tracing really is just like setting a point out from where you are as a vector and seeing what it hits at the end. And again, this is another thing that's just your life in 3D programming, where you're going to be just ray tracing all the time. To find out if something's on top of something else, you just ray trace down. Do I hit the floor? Yes, we're on top of it. No, we're not. Done. And rotations. So rotating vectors is a good time. The basic way of doing it is Euclidean angles, with radians or degrees, just rotated by that much on that axis. Unfortunately, it doesn't really work most of the time. I'll 2.5D as well. This is just something I wanted to mention in that something I want to kind of get across with this talk as well, which I will again come back to, and I keep saying that, is when you're writing your own games, it's best to start with something you can actually do and then work from there. So make your first game, if you haven't already, like a crappy arcade game. Make Tetris. I already did that. I showed it before. Why not? Like Tetris, it might not be a big project that you think will be super fun to do, but it'll teach you the stuff you need to know to move on from there. Then try making something like whatever came after Tetris, a more complicated game like Space Invaders or something. Not Space Invaders, sorry. What's one with the asteroids? Asteroids. Sorry. Eventually you might get to 2.5D games. I went there, I tried it out, so I'm thinking like Doom. If you know Doom, Doom isn't actually 3D, it's 2.5D. It was early 3D when they were working on that. The world isn't 3D, it's actually 2D plane that they project into 3D, so it looks 3D. Because there's no platforms, you can't go up and down. You can't have room above room, because it's not true 3D. It's actually like, if you're viewing it from above, everything's 2D. Anyway, 2.5D is doable for you guys. It can be. It'd take a little while to get there, but you can get there. And then after that, full 3D, why not? You can write all that stuff on your own. It's doable, it's just difficult, but you'll learn so much along the way. All this stuff I've just been blitzing through. The point that I'm going through is that these are just topics that you will hear talked about, and it's stuff that you will want to get familiar with, and things that you might be able to look at uni and courses you're going to and think, okay, how does that relate to game dev? Can I actually use that? Oh yeah, this is something that I heard talked about. But yeah, rotations, back to rotations. We'll rotate around, back to rotations. Euclidean rotations don't work in 3D space for this reason. So on the left we have a graphic of the gimbal, which is just a way to represent three axes of rotation. So we can use Euclidean angles to get facing in any direction, until we hit a situation which is in the right image, which is called gimbal lock, which is where 2 axes line up, and at that point you can no longer rotate in one of those axes. So in that GIF, the pink and green rings line up. Where's it going? It's gone. Did I remove the cable? Oh my god.
So this is the part where the axes line up. This is what happens.
Yeah, it broke the computer, so don't do that. Don't do gimbal lock.
Yeah, live stream's still going. This UQ system's just decided to pack it in. There we go.
I was going to say I could tell a joke otherwise, but okay, we'll keep going. It wouldn't have been a good joke. So gimbal locks just means that in certain situations, and it's pretty rare, but if it happens to you, you'll just be like, what is going on? Why can't I rotate this thing? What is happening? You basically lose a degree of freedom just because of coincidence of other rotations. So how do we get around that? In games, you might start doing it there's basically 2 ways you can do it. One is a rotation matrix, which is, we'll get to that, which is the more correct way of doing it, and is but is a bit slower. but rotation matrices are also complicated and not good to see for someone like you, maybe. So we'll do a quick detour into other topics because this is where this comes in. Quaternions, invented in 1843 by that guy, whose name I do not know, I'm sorry, as an alternative way of like representing number systems. He was trying to invent like his own number system. It was really strange. And all the mathematicians were like, this is kind of neat, but like also pointless. Like, why would you do this? It doesn't really make any sense. And it was like forgotten about for like 100 years, almost 100 years, until the 90s when someone was like, this would be really, really useful for doing rotations. And that's what they use them for now. Basically just in 3D applications, so games mostly, but also anything else 3D, like mapping and stuff like that. Quaternions are used quite often for rotations because they really, really handily handle rotating 3 axes without gimbal lock, using only 4 numbers instead of a rotation matrix. I won't get into how they work because it's really, really complicated. I'm sorry. You can look into it. I don't have time. Like, I would blur everyone's mind, including my own, if I tried. Inverse kinematics is another one of these. So this was invented in 1981 as a way for robot controlling. So if you do AI or maybe mechatronics courses like that, you'll learn about these. Robotics, yep. So on the left is an example of an inverse kinematic solution for robotics. But then what they did is in games, they were like, hey, this would be great for like putting characters' feet on the ground. So you might have seen in the game before when like your character's walking up steps, that their feet like automatically sort of land on the step and they sort of stop. Or they can be on a slope like this guy and the feet are sort of like sitting like that. Inverse kinematics is, well, kinematics is if you have an arm with a rotating part on it. If you rotate this part here, how does that affect joints that are further down the arm? Where do they go? Inverse kinematics is the opposite. So if I move my hand up here, how does that affect these joints here? Like what does that make this joint do? Move that arm like that, like that. So inverse kinematics is saying, if we put these characters' feet on the ground, by how we do that, we take the foot position, raycast down until we hit ground, and we just say, put the foot position XYZ at the position we hit the ground on the raycast, then apply inverse kinematics, and the rest of the limbs just sort themselves out. Like the knees will just move into position, everything works great. So a topic invented for robotics, and it's like used to make characters look a little bit better in games. You might have noticed like older games that don't do that, so it's a sort of a newish thing. And even a newer one is marching cubes, which was invented on the left as a way of taking CT data from like CAT scans and turning it into like a visualization to show a patient. So they'd use it for like ultrasounds and stuff like that. If you've seen those like kind of grainy medical renders, so marching cubes was invented for that. And we use it in video games now as a way. It's only been really very, very recent. After Minecraft, people were sort of into voxel stuff, but then they were like, how do we make our like blocky voxel world not just cubes, but like have a bit of slope between them? And marching cubes and its ancestor algorithm, marching squares, takes basically cubes or squares and softens out the edges automatically. So if you played a game that's like kind of voxel based, but you can also like dig a tunnel and it kind of forms out like an actual sphere rather than just blocks, that's marching cubes, and it was technology invented for CT scanning. So the point of this slide is I'm saying that a lot of game tech is like taking really high-tech stuff from other fields, even stuff that's been ignored, and applying it in a way to make things really efficient and just slightly better in video games. Physics. So physics engines. You might all know all these. Havoc's very, very famous, very popular. NVIDIA has their own physics engine. Bullet is ubiquitous. Everyone uses Bullet. It's everywhere. And that one up there you might not have heard of, which is Valve's attempt to replace Havoc. And they used it in Source 2. I don't remember what it's called, but apparently it's pretty great. Physics is one of those things that seems like a mystery. Like, how would you program physics? We're talking about performance and stuff. We want things to be happening at a crazy speed. How can we be simulating like bodies moving around and orbiting and like colliding with each other at real time? You may have done physics simulation stuff in some of your courses. Like I did a course where we did orbiting planets, and we were running it on like a supercomputer at uni, and you'd run it for like an hour, and it would give you like an hour's worth of simulation, and it would take it so long to get like a couple planets orbiting each other. So the key to game physics is optimization. Everything is just optimized. So here's a collision detection example. Scout from TF2 has some wacky hitboxes. I'm sure you've seen people complain about wacky hitboxes before in games, like, oh, it's not fair, like, how come these things line up this way, whatever. Hitboxes are used by physics so that we don't have to actually check where all the characters' geometry is. Otherwise it would be impossible. Like, the amount of detail in the scale, he's an old character now, so he's not that high poly, but even the polys in that's too much. So you want to just cut it down to the absolute minimum you can, and we just use boxes for that, because boxes are super easy to calculate as well. And then it's a matter of, as I said before, oct trees and quad trees. So this entire character would also be surrounded in one giant box. And if a bullet's coming towards him, we need to work out whether it hits him or not, or a ball or something. First of all, that ball ignores everything until it enters that giant sphere that takes the box that takes the entire character. It's like a bounding box. And then after that, it starts worrying about whether it's hit these individual parts. So really, all it is at the end of the day is just like massive optimization of every single point of the way. And I'm trying to just drill that home because that's just everything we do. Everything is just optimized continuously and like hacked together, really. Because as I said before as well, it doesn't really matter if it is accurate or not, as long as it's accurate enough and it looks cool and it's fun to play. People will be happy. So if you want to write your own physics, and I would say it's pretty fun, but also incredibly difficult, start simple and just try like basic gravity on rigid bodies. So they didn't start doing soft body physics until pretty recently. Rigid bodies is a much easier task, and I say that like easy. Again, as another quick aside, my company that I work for, True Axis, one of our main things is that we have our own physics engine, which is really cool. So I can't talk too much about it, but it's very cool. AI, this is the other big mystery in games, right? Physics, you're like, oh my god, physics, I couldn't program physics, but you can, it's just optimization techniques. Same exact thing with AI. If you've done AI at uni already, you would already know these things, but basically it all comes down to it being pretty stupid actually. And all it is routines and heuristics, and really only heuristics for things that like, there's only a couple of things you'd even heuristify, like pathfinding is a big one. We'll talk a bit about pathfinding, because it's the main thing you do as an AI in a game. And it comes down to navigation meshes, which are going to be, just like collision boxes, a way of simplifying the geometry of the level to make it easier for you to deal with it. So really, again, it's just a matter of optimize, and find cheap solutions to complex problems. So A-star search algorithms, you would have done this in AI. Basically, you have a heuristic that's just like get from A to E at the fastest speed you can, and you have a different weight to each of the paths along the nodes, and there's an algorithm to deal with that. You've seen that before. How does it work games? We just turn the geometry of the entire map into a graph with a what did I call it? I can't remember the word for it. Nav mesh. Yeah, nav mesh. So you can see we've broken everything into triangles, and the triangles would correspond to your nodes, and you give them a weight based on how big the triangle is. And it's like, you're done. Then it's just an A-star search algorithm technique. So you've turned the mystery of how does an AI know how to get from like here to the next room over there, going up and down stairs or whatever, into a search problem. And that's what you're doing, you know? You've just taken everything and turning it into an easy problem that you already know how to solve. Meta logic, multiplayer. I'm calling this meta logic because this is stuff that's like, it's not just logic in the game, it's stuff that you're like thinking about while you're writing the game, while you're writing the other logic. Oops. You would have seen this before too in games. I don't know what game this is. I don't think it's even a real game. But, yay, fun, right? Rubber banding. I think this is some dude's tech demo for some game he was working on. It looks pretty cool for a tech demo. But unfortunately his netcode is hot garbage. So I don't blame him. I would not want to be writing netcode or something like that. So rubber banding is what we saw. Multiplayer stuff, you would have done some server client stuff. It's not something you bolt on. Again, thank you Bethesda, thank you Todd. We tried to bolt multiplayer onto Fallout to their creation engine, it didn't go well. They got there in the end though, which is pretty cool. But the core of multiplayer in games is that the client is always going to cheat. The client is currently cheating, so just ignore everything the client tells you, except for raw input, and that's pretty much it. So your server, in a single player game, you give them the entire package, you can logic everything, they just run the game on their computer, the physics and whatever is running in real time. When you go multiplayer, that entire paradigm is broken because now the server is the only thing that you can trust. The server actually runs the game. The clients also run the game, but the version they're running is like fake. It's like a ghost world, it doesn't really exist. I'll get to UDP in a second. So the client simulates the game, they simulate their character running forward, whatever, when the player clicks forward. Then the data that they just inputted, so I press forward, gets streamed to the server. The server actually simulates it, they simulate the character moving. they take the output of that and send it down to the client. The client's already moved forward. They just ignore the server at the start. They just move forward a little bit. They get information back saying, you moved forward, and the client goes, great, I did, cool. Don't have to change anything. But if the server sends back info that says you didn't actually move forward, then the client has already stepped forward a bit. They just get thrown backwards, which is rubber banding. So in networking, TCP and UDP, you would have heard about this before. As I mentioned earlier, games are all about just speed over accuracy. So TCP is out, and we just do UDP, where we're just throwing data at the server, and it's throwing data back, and we do not care whether it's correct or not, because within like 0.001 seconds, we've already gotten new data back. So who cares about the old data? As I already said, trusted server, untrusted client. Frame blending is the main part of the netcode that deals with rubber banding issues. So the whole point of that is that your client is simulating the world based on the information it knows, and it only knows what the server's giving it as info or what you're pressing. And the server knows what every player is pressing and what they're doing all together at once, and is sending the correct data down to all the clients. And the client has to take the server's data and its own local data and blend them together and render the output in a way that isn't so jarring as your character zooming around all over the place, which is really difficult, really, really difficult. But that's called frame blending. And as I said before, I call this meta logic because you will rewrite your entire game from scratch if you try to add multiplayer at the last moment. It's not easy. Because your server as well, it'll be rendering the game and everything, it'll be doing all the actual game work, but it won't be rendering an output. So there'll be no visuals in your server because that will just slow you down. All you're doing is the game logic. So if you've got stuff tied into the render loops, again, well, you shouldn't do that. When you try to make it multiplayer, that's going to cause huge problems. Okay, finally, operation level optimizations. I mentioned before we're doing like large optimizations for the entire system. Operation level optimizations are the scary ones that you would know about and be terrified of, and completely rightfully so. This is the absolutely famous and infamous fast inverse square root. There's just like nonsense bit math going on in there. This was made for Quake 3. I think it was John Carmack. I can't be sure. He's like a super genius. He works for Facebook's 3D thing now, Vive, I think. He wrote like the Doom engine, the Quake engine from that. He basically invented 3D gaming. I'm pretty sure this was him or one of his programmers. But this is the sort of crap you have to do to make games work. Like nowadays, writing a game like Doom or Quake is a piece of cake. You can write it and you can run it on any computer you want. But at the time, they were pushing hardware to the absolute limit, and that's what people are doing now with cutting-edge games. But it involves nonsense like this. So fast inverse square root is just vector stuff. When you have a vector and you want to work out the tangent of the vector, the fastest way is to inverse square root. But doing square roots in code is really slow. There's no efficient way of doing a square root in maths. We've learned that in maths. So instead, we just try to avoid them at all costs. Square roots, so as an example, comparing distance. That's trig. If you want to work out the distance of something, it's a trigonomic equation, and normally that involves the square root of the hypotenuse, I think, which we don't want to do. So instead, you just, to compare distance, you take the two distances and compare them without doing the square root, because who cares? Like if you do the square root, you'll get a better result, right? But the comparison of the data without the square root done to it is the same thing as comparing with the square root. The numbers are off, but the comparison's all that matters in that case. So here, again, this is slightly wrong. The result from this is wrong, but it doesn't matter because it's close enough. And this is running like millions of times a second, you know? And this is for working out how to bounce a ball off a wall by calculating the tangent on the vector that you arrived at. And yeah, it involves ridiculous bit shifting with like magic numbers. No one knows how that works. So operation level optimizations, I won't go too much further into them because they're scary and they won't be relevant for you most of the time until you're doing like very low level optimization stuff, and you'll only be doing that in like functions that are running constantly. Like if you're writing your own physics engine, it goes in there. If you're writing really, really heavy stuff in the game loop, it goes in there. Some languages, creating objects is really slow, so avoid doing that. Reuse objects wherever you can. Like if you make an object, a new thing, just reuse it over and over and over again, who cares? Avoid inefficient language shortcuts. Arrow function loops are really slow in JavaScript. I only found this out recently. Like if you have a loop where you're going for all my objects, arrow function result, every time that loop runs, it recreates the function from scratch. So it's slow, write the function once, the long way, and put it in, it's faster. Also, this is the classic performance thing. Look for bottlenecks, fix them if you find them, otherwise don't bother. Cheap and good enough is better than perfect and slow 99% of the time, as I've already said. So as a wrap up now, I'm probably going a little over time, so I'll try to be quick. But making your own game. So start with something simple, as I said. Make a basic arcade game, but write it from scratch. Write the renderer yourself. Use a canvas in JavaScript. That's, you know, your outputs that are ready for you. Use a really basic graphics library in C++, something like that. Have a go at writing a basic render loop where you wipe the screen each time and you input new information each time, and you'll learn so much so quickly about graphics. And then work your way up. Start making more complicated things. Maybe throw in a really cheap 3D library, or, you know, try making a rotating cube game or something. And set small goals. And more importantly, keep trying. Nothing matters except your motivation. And I thought I had another dot point there, which is that your games will completely fail. I've worked on hundreds of game projects that went absolutely nowhere. It's completely normal. It doesn't matter. You learn every single one you try. You know, I wanted to make so many different games, and I started them and gotten like 2/3 of the way there, or 1/3 of the way there, and just gotten bored and stopped. Whatever, like, it doesn't matter. Like, no one's going to play them anyway. And I learned so much doing that eventually, you know, I got a job in the industry. So here's an example of the game I made very quickly. We can cut to a live example after the talk, but here's just a screenshot. Not mine on the left. That's that's an actual bit of footage from Rosetta mission, I think, from NASA, when they landed it. Oh, from the European Space Agency. They landed a probe on an asteroid. That's an asteroid rotating around the sun somewhere. That's what it looks like. Blew my mind. So I was like, I want to make a little game set on an asteroid. And I started one, and that's basically as far as I got. There was some like Lovecraft stuff going on, whatever. But it was really, really cool, and I learned a lot of cool stuff doing that. And it's like a 2.5D game. And then I used that same engine to later start writing a RTS engine in JavaScript, which is currently, that's an earlier version of it. That's that shader I showed you earlier, is doing that water. There's a later version of it. I can show you live later, but not important. And so now we get on to the final part, right before I finish. Games industry in Australia. If you're interested in entering the games industry, we'll get to that in a second. First of all, these companies here all have something in common. They're all Australian, and they all made a pretty big game, or big games. 2K Australia, huge. They made a bunch of Bioshock games. They helped out with them, I mean, including Bioshock 2, Infinite, further games. They made some Borderlands stuff. They made Borderlands the pre-sequel, which, have you played? I don't know if you've played that. It's not great, honestly. Didn't sell well. The company died immediately after making it. Poor 2K Australia. Team Bondi was in Sydney. You remember LA Noire? You probably remember some controversy around Team Bondi. Same sort of thing. Their game came out, didn't sell well enough, and they died. They were going to be Rockstar Australia. They were in talks, but something went wrong. Infinite Interactive, you probably haven't heard of it, more obscure, but I love that game, Warlords Battlecry 3, I love it. It's so weird and obscure, but it's an RTS game. They're in Melbourne. They still exist, but now they make like Candy Crush games on mobile. It's a bit sad. Sledgehammer Games in Melbourne as well, I think. They work in the Call of Duty mines. They make Call of Duty content, like they just churn it out, good on them. They're always hiring. So a lot of artists mostly. That's my company, True Access, True Skate. Look it up, you'll see. It's like #1 on the App Store. You won't believe it, but you'll see it. Wargaming Sydney, they also hire a lot. They make World of Tanks. Their main thing is like an engine or something. They do like more than actually a game, it's something else, technology involved. They're also hiring a lot. They own a museum of tanks in Cairns, I've been there. They built this museum, they paid for all these tanks to get shipped there so they could use them as references for their game. Then there is, these ones here are all Brisbane games, Brisbane Game Studios. We do have an industry. I'll start with the ones that don't exist anymore though. So, THQ Studios gone, Pandemic gone. They made big games, they were huge. They were our biggest studio, Pandemic. They made Star Wars Battlefront 2, the original. They made Destroy All Humans and a few other things. They died in like 2005 or something. The monkey in the bottom left, Defiant Digital, was made up of remainders of Pandemic. There's also a lot of Pandemic devs in Brisbane. You will meet one eventually. You will. If you go into industry, in any industry in Brisbane, you will meet Pandemic devs. They're everywhere. Really cool. They made that game company, Defiant, who survived a little bit longer, died in 2015. Can't remember why. There's Chrome. Splash used to be called Popgun. You might have heard of Popgun. Now they're called Splash. They make games now. Gameloft, always hiring. Has had a really bad reputation for worker crunch and stuff, but apparently they're getting better now. Half Brick, opposite, used to be really great, apparently pretty bad now. Obviously, they made Fruit Ninja, you know them. And Webbed, I put in there is an indie game. I only put it in because I know the guy who made it, and it came out like a month ago. Very new, hitting up the Steam charts. That was made in Game Maker, so that's another option. So the games industry, the bad news, sadly, is that, well, good news, it's growing, right? It's getting bigger, especially in the pandemic. Sales are going up a lot. Companies are hiring. But it is really, really hard to enter the games industry. Like really, really, really hard. It's easier as a programmer, but it's never going to be easy. I have a statistic that I wrote down from a Commonwealth report from 2016 from the Department of Environment and Communications, which said that there are currently 5,000 graduates a year in games courses in Australia, and there are total 1,000 people employed in games. 5,000 grads a year, 1,000 jobs total. It's not great. I'm one of those 1,000, yay! But, and I didn't do a games design degree, so my point is that you don't have to, and you're probably at a better position as a programmer than a games design graduate, because you're not going to get another job with that degree. With a programming degree, you can do anything. Anything with computers. Make it happen. So, as I've been saying, it's just about writing your own games in your own time, learning, being interested, and if you really care about it, you will sort of make it happen. You'll, work on it as a hobby, you'll learn so much along the way. About graphics, about programming, about optimization especially, and all these things are relevant in any industry. There's a lot of stuff going on in graphics that isn't games, like in 3D rendering, in visualization stuff, in mapping stuff, in all sorts of industries. And it's also just a really fun project to do in your own time. It's a fun hobby. Like, you might have seen people say, program in your own time as a way to increase your skills, and they recommend things like making an app that's like a note-taking app for yourself. That's pretty boring, right? Wouldn't you rather make a cool game that you've been thinking of making for ages? Wouldn't that be more fun? And this is my main project that I want to finish in like 5 years or something, that I've been working on for like 3 years. But this is my ending slide there. That's pretty much everything. I'm happy to answer any questions you have, or I can show live demos of my other games and the code behind them if you're interested. Otherwise, the pizzas are probably getting cold, so go ahead. Take a question.
Just a quick one. At the start, you were talking about the importance of optimizing for speed, obviously, especially these first-person shooters and whatever.
Yep.
What if you've got like a turn-based game, the likes of Civilization type thing? I get the feeling that in that you want to optimize to reduce the time between turns, so
yep.
You're not waiting around to hit the next turn, so you get your hits.
That's pretty much it. If you've played Civ before, have you played Civ on like an old computer and then bought a new one and played it again? And you'll notice that like a game is like 20 minutes faster. I noticed that. When I bought my 1080, which was the best graphics card ever at the time. I was playing Civ 5 like the year before, and a game would take me like an hour or two to play. And after I bought the 1080, the same game would take me like 40 minutes, just because the turns are faster. And yeah, so during like scrolling around the map during your turn, the game's not doing much. I'm sure it's doing whatever it can in the background to get ready for the next turn. Like it's just filling arrays, doing whatever crap it can to like make sure everything's as fast as possible. But when you click next, it has to run through thousands of like checks and routines and stuff. And they try to make that as fast as they can to speed those times up. Because waiting for the next turn is boring.
I think in Civ 6 they have an option where you can work through and run a stress test on your game.
Yeah.
And it makes like maximum civs, maximum everything on the hardest difficulty. So it's all competition and the civs attack one another.
Yeah, yeah. It's like if you watch AIs just fighting each other, that still takes forever to run through because they're just ticking through like thousands of things happening all the time.
One last quick one is, when you were talking about the games on a server, where basically the server has the real game and so on,
yep.
Does it purely have entire control, 100% over that, or does it have like a consensus mechanism from all the inputs, like some, a bit like a crypto thing we'd say, okay, all these people said what you did checks out, so I'll take that, or does it just absolutely ignore everyone and say...
Yeah, those are totally two different ways of doing it, and it depends on the game and the exact situation you're in. I've heard of games doing that, but more common is the single source of truth, server does everything, clients don't have a say. Yeah, just because cheating. And like in a lot of applications, you'll write stuff with multiplayer, with servers, like in a web application or whatever, you'll write stuff with the idea that the client might send bad data and you don't want to deal with that. Games are one of the few places where you know the client is sending bad data because people will try to cheat constantly. Like there's no game out there where people aren't constantly trying to bot it or cheat it. So like you can deal with that consensus stuff, and it works especially for like peer-to-peer, like RTS games or something where you have two players that are just playing against each other. They might work on a consensus sort of situation, and that also helps with the frame blending because both sides are sort of agreeing on what's happening. But with a huge game, like if you imagine Battlefield with like 64 players, it's just the server who knows what's going on. All the clients are just like getting fed and feeding back
I
info.
suppose it probably takes too long to consider lots of options, doesn't it?
Yeah, exactly.
Even if you wanted to, you might just pull a couple, and then
Yeah.
it would get sketchy as well.
So they show people are just gagging like 55 other players are cheating. And they're all
Yeah, exactly. I mean, if there is a way you can cheat with it, then someone will. So. Or many people will.
Would games like Battlefield work on a single server system? Like, do they run on a single machine that serves 64 people, or do they try and spread like really single machine?
Yeah. They'll have physical servers. Like there's Australian servers for Battlefield. Those servers will be in Sydney somewhere, and they'll just be an actual machine just there. That's just sending data as fast as it can to those 64 players and taking back information from them and discarding half if they've been cheating. But yeah.
team of people fanning it.
Yeah, pretty much.
Well, if nobody else has any more questions, token of appreciation for your talk.
Oh, thank you very
Thank
much.
you, Will. Yeah,
That's for the viewers at home. So.
yeah. It's kind of interesting. So many like intelligent people work on this. Also, it pulls from so many different fields. The games sort of just like hijack.
Yeah, exactly. That's one thing. I wanted to talk about was that. Yeah, it's like some of the smartest programmers work on games, and the people who work on games, it doesn't pay more than other things. That's something else to mention too. It does not pay more than other industries. You do it because you love it, and people work on games because they actually like enjoy doing it. That's why I work on games. So like you get a lot of smart programmers who are motivated and aren't just there because they're getting paid like hundreds of thousands of dollars. They really want to solve these problems because they think it's fun to make, you know, Call of Duty or Fortnite or whatever.
It's kind of awesome.
Yeah.
Yeah. No more questions from anybody?
One thing I will say is that we had a talk on fast inverse square root for UKCS a couple months ago.
Wow.
It's actually a pretty decent explanation of it. It acts as a square root by approximating it as a logarithm or something.
Yeah, wow.
The talk is on our YouTube if anyone wants to find it.
Cool. I would recommend checking that out then. Why not?
Sweet. All right. Well, that ends the talk. We do have pizza. I suppose we'll just head out the front and chow down on that. Obviously, you're free to hang around and have pizza, of course.
Yeah.
But yeah, thanks for coming, everybody. Pizza out front.
Thank you.